Hello everyone, I am Giridhari. I am an assistant professor in the Department of Applied Science, Haldia Institute of Technology. Today I am going to discuss about sequence and series part 1. So first we have to know that what is a sequence. So sequence is nothing but a mapping from natural number set to real number set. That is, a sequence corresponds to every natural number to a unique real number. So there are many types of sequences are there. They can be finite or infinite. Infinite sequence is our debate of discussion. So, if terms of a sequence can be defined as A1, so terms of a sequence can be defined as A, A1, A2, A3, or infinite sequence. Now, this is a sequence and this can be denoted as A n in the second bracket. Okay, if n is equal to 1 by n, so first term will be n equal to 1, that is 1. The second term will be n equal to 2, that will be 1 by 2. The third term is n equal to 3, that will be 1 by 3, and it goes on. So every natural number n, we can get a real number in the real numbers. Okay. So for n equal to 3, we get 1 by 3. For n equal to 2, we get 1 by 2, and so on. Okay. Now, the sum of the terms of the sequence is called infinite series. The sum of the terms of a sequence is called a series, and infinite series is our debate of discussion. Now, we have to know about different types of sequences. Now, there is a question, what is monotone sequence? So, if the next term of a sequence is always greater than or equal to the previous term, it is called monotonically increasing sequence. Let's say n is a sequence. Now, if the term n plus is always greater than equal to an for all n belongs to the natural number set, then it is said to be monotonically increasing sequence. Now, if an plus 1 is strictly greater than an for all n belongs to the natural number set, then it is said to be strictly monotonically increasing sequence. Now, if the next term is always lesser than or equal to the previous term, then it is said to be monotonically decreasing sequence. And if mathematically we can define an plus will be always lesser than equal to an for all n belongs to the natural number set. Now, again, if an plus 1 is strictly less than an for all n belongs to the natural number set, then it will be a strictly monotonically decreasing sequence. Now, these are some examples. Here n is a sequence, and if n is equal to 2 to the power n, then the sequence n will be in this form. If n equal to 1, we will get 2. If n equal to 2, we will get 2 square, that is 4. If n equal to 3, this will give 2 cube, that is 8. If n equal to 4, this will give 2 to the power 4, that is 16, and it goes on. So, 4 is always greater than 2, 8 is always greater than 4, 16 is always greater than 8. So, next term is always greater than or equal to the previous term. Again, here an plus 1 is strictly greater than an. That is, the next term is strictly greater than the previous term. So that's why it is also a strictly monotonically increasing decreasing sequence. Now for this case, the sequence will be when n equal to 1, the first term will be 1. When n equal to 2, second term will be 1 by 2. When n equal to 3, third term will be 1 by 3, and it goes on. So here 1 by 2 is actually less than or equal to 1. 1 by 3 is actually less than or equal to 1 by 2. So it is actually gradually decreasing. So that's why it is a monotonically decreasing sequence. It is not only less than equal to, but also less than the previous term. So an plus 1 is strictly less than an for all n belongs to the natural number set. So that's why it is not only monotonically decreasing sequence, but also strictly monotonically decreasing sequence. Now, if we choose this sequence, the third one, then here n will be minus 1 to the power n. So the sequence will be, first term will be minus 1, the second term will be minus 1 to the power 2, that is 1, the third term will be minus 1 to the power 3, that will be minus 1. So this is again 1, this is again minus 1, equals 1. So here next term is greater than the previous term, but in the next case, next term is actually less than the previous term. That's why it does not follow any kind of properties here. Neither n plus 1, neither n plus 1 greater than n, or neither n plus 1 less than n. So that's why it is not a monotone sequence. If a sequence is either monotonically increasing or monotonically decreasing, it is said to be a monotone sequence. If a sequence neither monotonically increasing nor monotonically decreasing, it is said to be a non-monotone sequence. Now we come to the bounded and unboundedness of a sequence. If there exists a upper limit of a sequence, that is, if the every term or every element of a sequence is less than equal to some number n, for all n belongs to the natural number, for all n belongs to the natural number, then it is said to be bounded above. Then it is said to be bounded above. For this sequence, the terms are 1, 1 by 2, 1 by 3, and it is goes on. So here, every element of this sequence is less than equal to 1. Every element of this sequence is actually less than equal to 1. So this is actually bounded above. Now, if a sequence has a lower limit n, that is, if every element of a sequence is greater than equal to something, then this will call a bounded below sequence. So for this sequence, this will be 1, second term will be 4, third term will be 9, and so on. So every element is greater than equal to 1. So that's why this sequence is bounded below. Now a sequence is said to be bounded if it is both bounded below and bounded above. So if we take example n equal to minus 1 to the power n, so every element of this sequence lies between minus 1 to 1. That's why it is a bounded sequence. Now for this sequence n equal to 1 by n, the elements are 1, 1 by 2, 1 by 3, 1 by 4, and goes on. Goes to infinity. So all the elements of this sequence lies between 0 to 1. So it goes to actually 0. That's why the elements of that sequence lies between 0 to 1. Now, if n equal to n square, okay, if n equal to n square, this will be bounded below but not bounded above. That's why it is an unbounded sequence. Now, 1 one question may arise when a sequence actually tending to a point or goes to infinity or goes to minus infinity. So to answer this kind of question, we have to know the limit of a sequence. So a sequence is said to tend to a limit L if for every epsilon greater than 0 there exists a positive integer n such that mod of a minus n less than epsilon for all n greater than or equal to n. Here a is a natural number. Now, if for a sequence n equal to 1 by n, we draw a graph, we can see that this is the n values and this is the n values. This is the n value, that is the terms of a sequence, and this is the n value, that is the natural numbers. Okay. So, if n equal to 1, the value of n is 1. If n equal to 2, the value of n is 0.5. Okay. If n equal to 3, n will be 0.3 and it goes on. Okay. We can see in the graph clearly when n greater than 80 or 100, the sequence is actually tending to 0. So, if we draw a neighborhood at 0, we can get infinite number of values of that particular sequence n equal to 1. Okay. So, a sequence is said to be convergent if the limit of that sequence will be finite, and a sequence is said to be divergent if the limit of the sequence will be finite or will be infinite or minus infinite. Okay. So again, a sequence is said to be convergent if the limit of a sequence will be finite. A sequence is said to be divergent if the limit of the sequence will be infinite or minus infinite. Okay. So now come to the next slide. This is the classification of a sequence. So a sequence can be divided into two sections: bounded sequence and unbounded sequence. A bounded sequence either will be convergent sequence or oscillate finite. What is oscillate finitely or oscillates infinitely? An unbounded sequence will be either divergent or oscillately infinite. So, if a sequence is neither convergent nor divergent, this will be said to be oscillate finitely or oscillate infinitely. That is oscillatory sequence. Oscillatory sequence. Now, for this sequence, we have n equal to 1 by n. So, limit of this will be 0. 0 is finite. That's why it is convergent sequence. Here n equal to minus 1 to the power n. This will give minus 1 comma 1 comma minus 1 comma 1 comma minus 1 alternatively. So here there is no such limits are there. There are limit points 1 and minus 1. That's why it is also bounded. That's why it is oscillatory finitely. It is neither convergent nor divergent. That's why it is oscillatory finitely. And the limit points are 1 and minus 1. That's why it is oscillates finitely, because limit points are finite. Now, if we take this example, n equal to minus 1 to the power n into n. So the limits of that sequence actually goes to minus infinity and plus infinity. That's why it is called a oscillatory infinite sequence. If this the limit of that sequence goes to infinite or minus infinite, then it will be a divergent sequence. But it is actually going to minus infinity and plus infinity. Okay. Now for this sequence, the limit will be log 1, that is 0. So this is a convergent sequence. Here n equal to n square. This goes to infinity. This goes to actually infinity when n tends to infinity. So this is a divergence. Now we have to know what is an infinite series. So previously you have mentioned that an infinite series is the sum of the terms of a sequence. So this can be written in this form: s equal to s a1 plus a2 plus a3 plus dot 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 goes on, where a1, a2, a3 are the elements of an infinite sequence. Now the first n terms of an infinite series, the first n terms of an infinite series, the sum of the first n terms of an infinite series is called partial sum. The sum of the first n terms of an infinite series is called partial sum. This can be denoted as Sn, which is equal to a1 plus a2 plus dot 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 a. These are the first n terms. Okay. Now sequence Sn, which is called sequence of partial sum. Okay. So this can be denoted as a sequence, and if limit n tends to infinity Sn is finite, say S, then the series will be a convergent series and converges to that limit S. Okay. Now, if Sn does not approach to a finite limit, or it will give some infinite or minus infinite value, then it will be a divergent series. Okay. So these are some basic series. This is geometric series and this is P series. If we have a geometric sequence which is a comma ar square 1 dot dot dot, where r is the common ratio and a is the first term, then we can have the geometric series in the form as s equal to a plus ar square plus ar cube and go on. Then a is the first term and r is the common ratio. So this kind of sequence is said to be convergent if mod of r less than 1 and converges to this value, where a is the first term and r is the common ratio. And this kind of sequence will be divergent for mod r greater than or equal to 1. Now this kind of infinite series where n is 1 by n to the power p, this kind of infinite series is called P series, and this kind of series will be convergent if p greater than 1, will be divergent if p less than or equal to 1. Now to observe or to notice the convergency of an infinite series, we have some tests. Okay, so this is a comparison test where an and bn are the infinite series of non-negative terms, and 0 less than or equal to an less than or equal to bn for all n belongs to the natural. Then if bn converges, then an is also convergent. If bn converges, then an is also convergent. And if an divergent, then bn is also divergent. Okay, so these are some tests. Now there are some examples. So where we can see that here this is the geometric series and r equal to 1 by 2, and here this lies between mod of r less than 1, that is it lies between minus 1 less than or less than 1. So this is a convergent series. This is again a geometric series where r equal to 1 by 3. This is again a convergent series because here r equal to 1 by 3, which lies between minus 1 less than or less than 1. Here this is a NP series where this can be written in this form where n to the power p, here p is equal to 2. Now when p greater than 1, this will be convergent series. This will converge when p greater than 1. We have the value p is equal to 2. So that's why 2 is greater than 1 actually. So that's why it is convergent. And this is again a NP series where p is equal to 1. And we can see that this sequence will be divergent if p less than equal to 1. So that's why it is a divergent sequence. This is a divergent sequence. Okay. So in the next part, we will be covering some tests related to convergency of infinite series, D'Alembert tests, Cauchy group test, etc. Okay. To be continued. Okay.